Before we jump into the math that's involved in this section, I want to talk a little bit about what exactly is pressure. I don't think that you have probably too much trouble understanding volume, and I don't think you have too much trouble understanding temperature, because those are concepts that are pretty familiar to us. But pressure is a little bit different. This barbell here probably weighs about 15 pounds. I'm not sure exactly. I know each of the plates is 5. I'm not sure exactly what this weighs. But I'm using it as an illustration because it's pretty close to the weight of the atmosphere that's pushing down on every square inch of your body all the time. Because normal atmospheric pressure is 14.7 pounds per square inch, so approximately the weight of this thing. And that feels pretty heavy. So let's say that we have maybe approximately a square inch here pushing down on my hand, and you can see that that's making a little mark on my hand. And that's a lot. But we have that all the time, every day, pushing down on every square inch of our bodies. And that's because we have all this air around us on the earth that goes up miles and miles and miles. And we don't think of air as weighing very much, but when you have that much air, it adds up. And that's because air is made of little particles. And those little particles are either atoms or molecules or sometimes ions, but they all have mass. And if you have a column of air that's miles high, it does add up after a while. And the gravity's pulling down on that, and it's putting pressure on you, on the ground, on whatever. So we have all this atmospheric pressure coming down on us. Now in a container, which is what we're mostly going to be talking about in this chapter, let's say we have gases trapped in a container like this. And this looks like it's empty, but it's not empty. It's got air in there. So if I open it up, we can make sure that the pressure in here is equal to the pressure out here. Put the cover on it. So now this has approximately 14.7 pounds per square inch of pressure in here. And that pressure is pushing against all the surfaces. This one, this one, this one, everywhere, 14.7 pounds per square inch. Now the reason that doesn't make this thing explode is because we've got 14.7 pounds per square inch also pushing on the outside. So we've got pressure from the outside and pressure from the inside, and they equal each other out, and so nothing happens. Now if we were to make the pressure in here a whole lot higher, then this thing would kind of expand until finally it might explode. Or if we were to make this a whole lot lower, you might see it collapse on itself. And we'll do an experiment in class or something like that. But what exactly causes that pressure? In a container where we have gas molecules zipping around really, really fast, these gas molecules are trapped in there. And gas molecules at normal temperatures are going hundreds of miles per hour. Now, it kind of depends what the temperature is. Obviously, higher temperatures would make them go faster. And it depends on how big the molecules are, because bigger molecules will go a little bit slower than smaller molecules. But anyways, we've got all these molecules in here, and they are zipping around super fast, like hundreds of miles per hour, and they're crashing into the sides. And that's what's happening. So all these molecules are banging against the sides of this container continuously, and that's what causes the pressure. And then on the outside, we have all these gas molecules banging against the sides of the container continuously, and that causes pressure on the outside. And there's so many molecules so fast and so hard all the time that that causes all that pressure. And if you think of a balloon being blown up, you know, the balloon's just kind of this little floppy bag when there's no air in it. But you blow it up and it's, you know, this very tight latex bag. And the reason it does that is because you've put lots of air molecules in there that are moving very fast, and they're crashing against the walls of the balloon all the time. And the balloon can't collapse because these molecules are always pushing on it from the inside. They're pushing it out. And it seems like we ought to be able to see it be lumpy, but there's just so many molecules that are pushing all the time, and they're so very small that it ends up giving a smooth appearance. If we could see on that tiny little level, we'd probably see it be lumpy. But it's those molecules that are pushing against the walls of that balloon on the inside that's causing that pressure. So now that we have some idea of the concept of pressure, let's look at something called Boyle's law. And this is totally intuitive. Think about this. Think about if we had a different arrangement. Now this is a rigid container with a cover that cannot change its position. So use your imagination for just a second and picture this as if it was maybe a syringe or a piston kind of thing, where the cover could move down and move up. You know what syringes and pistons act like, and so it changes the volume. So if we move the piston down, so let's say I have air trapped in here, and I have a cover that's up here, and we have some amount of pressure in there. Maybe it's normal atmospheric pressure of 14.7 pounds per square inch. Now, if we use a different unit, there's a unit called atmospheres, and that's a little bit easier because normal atmospheric pressure is 1 atmosphere. So it's easier to talk about. So let's say it's 1 atmosphere of pressure in here. And then let's say that I push down on my piston, so I make a smaller volume. So now all the gas molecules that used to be spread out this much are now squished together in less volume. Would it make sense to you that there's going to be higher pressure in there? Because now these gas molecules are squished into a smaller volume and they are going to crash against the walls even more often than they did before. And so we're going to get more pressure in there. And I think that kind of makes intuitive sense to you. If you think about taking a syringe, and we'll be doing this in one of our labs in class, think about taking a syringe and pushing on the plunger and making the volume smaller. You have to push on it and you feel the pressure pushing back against your hand. And so that makes sense. Well, Boyle's law says that pressure and volume are inversely proportional. And what that means is that you increase one, you decrease the other. So mathematically, that looks like this. So P stands for pressure, V stands for volume. You can use any units of pressure that you want. We'll be introducing quite a few different units in class. And you can use any units of volume that you want, as long as you keep them the same on both sides of the equation. So what this is telling us is that let's say we have situation number 1, where the volume is like this. And so we would have some amount of pressure, and in my example I said that was 1 atmosphere. So let's substitute that in, 1 atmosphere for P1. And the volume, now I'm going to have to guess. No, not really, because it says it. This is, oh no, that's weight. Never mind. We'll have to guess. Let's say that this is 500 milliliters. That'd be close enough. All right, and let's say that I'm going to reduce the volume in half. So I'm going to push my piston down so that the volume of my gas is now half of what it was before. So I am asking the question, what will the pressure be in there? And maybe you can just intuitively figure this out. If you're going to have half the volume, you might have twice as much pressure. And if you knew that right off the bat, that's good, because that means you have a sense for this concept. Sometimes the math won't be quite this easy, so we'll run through the math just to make sure. So let's divide both sides by 250. So 500 divided by 250 is 2, and 2 times 1 is 2. So now we've got 2 atmospheres being equal to the pressure after I make that change. So that's what Boyle's law is all about. Now sometimes you have problems that have harder math in them, but you have a calculator so you can do that. But essentially, that's all that Boyle's law is. You look at what is the scenario before you make the change, what is the scenario after you make the change, and assign 1s and 2s. Now sometimes if you're using pistons, it's handy instead of using 1s and 2s to use top and bottom, to say P top, V top, and then maybe you're pushing the piston down close to the bottom and you can use P bottom, V bottom, and that sometimes makes the problem a little bit easier to solve. But essentially this is a fairly straightforward law and not too difficult to use.